Greetings, folks. I thought I'd put on here an interesting calculation. It's a calculation that's not very accurate, but it's certainly of historical significance, and it's Hartree's original treatment of the helium atom. And it's his ingenious and very simple method of dealing with the electron-electron repulsion term. I've taken this out of Charles Quinn. It's one of his examples he does using Microsoft Excel, and I've just taken it from there and put it into Mathematica and then done a thing or two with it that we'll see here. What I like about it is its simplicity. It's not Hartree-Fock, it's just Hartree. It does not take into account anti-symmetry or the Pauli exclusion principle. There's no Slater determinants. It's much simpler than that. And as far as I know, it only works analytically here for the helium atom. But it's an interesting calculation. It certainly gets us in the ballpark. So I thought it was worth putting on Mathematica here that makes the equations a little clearer than looking at the Microsoft Excel code. So here we go. We start off here with a parameter called K. This is an adjustable parameter that we will we'll set it later so that we can minimize the total energy. For now, we just have kind of an arbitrary starting value here of K equals 2, so we'll start with that. Then we go through a series of 5 different equations here that are discussed in Charles Quinn's computational quantum chemistry in there. So I'm not going to go over the discussion of them, except to point out his treatment of the 2-electron term. It's this term here called F0, and it is based on whatever value you put in for the K parameter here. There are 5 equations we use. I've numbered them here 1, 2, 3, 4, or 5, as well as the equation numbers taken out of the text in Quinn. So they are to be used in that order. So going through the first time, it wasn't real clear the order to do that until I kind of sat and thought about it a little bit and looked over his Excel code. So I've labeled them here very clearly, steps 1 through 5. So the nitty-gritty of those equations you can look at in Quinn's book. But here they are. They work fine. They're simple. Just type them out. They're one-line equations. And then we calculate the total energy for the helium atom, and we get a negative 2.375. Now, of course, that's quite far off from the correct value of around minus 2.9 something. But then keep in mind, too, we just kind of made up a K value here. Just made up anything to get the calculation going. So we don't expect anything very good here. But yeah, we get a total energy of 2.375. Also put in here just a direct calculation of the, well, I don't know what you might call the core Hamiltonian, the kinetic and potential energy terms. Just put in the typical way a person would calculate those and put those in. It works out the same. We add that to our Hartree electron-electron repulsion term F0. We get the same minus 2.375. So that was the kind of little check I put in to get the kinetic energy, potential energy there, and kind of 2 different ways, using 2 different formulas. So then what we want to do is find the value of K that will minimize E. Value of K equals 2 gave us a total energy of minus 2.375. So we want to optimize that. We want to minimize K. Sorry, we want to minimize the total energy by varying K. So I did that here on Mathematica. I used a method called the secant method. The secant method is a fairly basic, commonly used root finding technique that drives anything you want to 0. So what I want to have 0 here is the first derivative of energy with respect to K. I want dE dK to be a stationary point. So it's dE dK that I want to use the secant method to drive to 0. But I don't have, of course, any analytic way of calculating dE dK, so I used a numerical approximation, kind of a central finite difference approximation for the derivative here. Number of ways you can do it. There's right-hand derivatives, left-hand derivatives. I used a central one here to seem nice and symmetric. So what I want to do is drive dE dk to 0 using this approximation for it, where a delta k is a small value. The smaller the better, really. So I used a value of 0.01. The secant method, the details, the formula for that you can find in any numerical analysis textbook. It's a very commonly used way of finding roots of equations. So we're going to use it to force dE dk to be as close to 0 as possible, and presumably that'll be where the energy is a minimum here. We'll assume that's what happens. So if you've encountered the secant method before, the good thing about it is it doesn't require having an analytic derivative of your function. The bad thing is it requires two initial guesses because it's a secant deal rather than a tangent deal. So you need two initial guesses. So for the first one, I just used our k value of 2 that we used here before, and then tweak it a little bit to evaluate the derivative, add and subtract delta k to it, calculate the total energy terms, and then use those to estimate my derivative dE dk. This is my first estimation of dE dk, so I call it dE dk 1. And it gives me minus 0.6875. It's kind of far off from 0. A secant method does require I have a second initial guess, so you could do pretty much anything here, 1.9, 1.8. I just did 2.1. Nothing special about that, just something to get a second value here. So I use 2.1. Go through the process again, add and subtract my delta k value of 0.01, and then from that then I can estimate my first derivative again, my dE dk. Again, get minus 0.6375. So now we can use the secant method formulas. So here it is to get the third estimate. I had two initial estimates. Now I can use the secant method formula to get the third estimate. Call that K3. And then I need to use that to estimate the derivative. So add and subtract 0.01 to it, calculate the values, estimate the derivative again. And then I guess I was quite surprised at this point. The value for the derivative came out with an exponent of negative 10. I mean, that's pretty much 0. That's pretty much there, and that's just what I wanted it to be. I thought I'd probably have to go through and do a handful of iterations here. I didn't expect it would just converge like that the first time around. So it's incredibly fast convergence, but there it is. The first derivative, dE dk, is 10 to the minus 10th. So that's good enough for me. That's a good convergence. So that converged then. When I print out the k value, that at this point is 3.375, and then the minimum energy that k value gives me is negative 2.84763, which isn't super good, but then considering how simple this method is and considering how we didn't do any real kind of self-consistent field, iterative sort of stuff, a very simple calculation, negative 2.847 versus the around minus 2.9 we're supposed to get, is pretty darn decent results for such a simple algorithm. So hats off to Hartree for working this out a long time ago, and also to Quinn for illuminating this interesting calculation in his book. So hope you find it interesting. Thank you for listening. Hope to see you in another video. Goodbye.